Welcome to the Society of Amateur Radio Astronomers, Radio Astronomy, Constant Variables and Formulas. Lesson 8, RF COAX, Cable Loss Interpolation. Coax cables are used in radio astronomy for short connections between components and long connections for the antenna system to the receivers. The cable manufacturer provides a table of cable characteristics that show the measured value of cable attenuation, usually in dB, at different frequencies. This exercise shows how to interpolate the table values for your specific RF setup. Also, along with the cable, you have connectors on each side. The two common connectors that are used are a high-frequency connector called an end connector, which has a 0.15 dBi loss at 15 gigahertz. The UHF connector is SO239. It has a larger 0.5 dB loss at 432 megahertz. It is therefore important to limit the number of connectors in your cable string. This is an example of a table from an organization that shows the attenuation in dB per 100 feet. Notice there's a cable group, then there's the frequency band going across the top. The number in the table is actually the dB loss per 100 feet of cable. We're going to transfer that over to a Excel file. And you notice that I've got the cables all grouped, frequencies, then the attenuation from the table. This makes it easier to plot. So we take that plot and we're going to go add a scatter chart. You do that by selecting the data. So you'd go from the frequency attenuation and select that. You'd go over to scatter and insert scatter and select the scatter with smooth lines and markers. You'll end up with a blank plot on your screen. You select the data, come up with this chart it'll add, then you go ahead and add the series name. Say we're going to use the LM100A data, and then you select the data in one column, you select the data in the other column, hit OK, and then that'll give you this output. Hit OK there too, and it'll come up with this plot. You'll have to go to the plus sign on the right and add axis titles, and that'll allow you to put the titles on the bottom and the vertical and on the top. To add a trend line, you go down and click the trend line mark. It'll say add trend line. And then you do a couple other things. One is you'll select the trend line type of equation. This, you can go through the list and see which one clicks better. This one actually worked the best with the power. Then you display equation on chart and display the R squared value on the chart. Note that R squared, when it equals close to 1, is the best fit and shows you have a good fit for the model. If it's a lot smaller than 1, then you have a bad fit, and you probably should go to a manual method, which we'll show at the end of the slides. This is an example of plotting LMR 100, 200, and 240 and 400. This is frequency on the bottom and attenuation loss per 100 feet of cable length. Example 1. The cable will be the LMR 400 at a frequency of 1420 megahertz. Cable length will be 80 feet. You pull your equation for the LMR 400 cable from the right. Then you take the value that comes up with, and that'll equal 4.94 dBi per 100 feet. Now, the dBi loss at 80 feet, you multiply that number times 80 feet, that'll equal 3.95 dBi. If you add the two end connectors, which are at 0.15 dBi per connector, the total dBi loss for the 80 feet of LMR 400 cable at 1420 megahertz is equal to 4.25 dBi. Let's do another example using LMR 200 cable, frequency of 1260 megahertz, and a cable length of 20 feet. Take your equation from the right. dB loss, if you plug that equation in, will equal 11.7 dBi per 100 feet. Your dBi at loss at 20 feet is equal to 11.7 dBi times 20 feet over 100 feet. It's equal to 2.4 dBi. Add your two end connectors at 0.15 dBi per connector. Your total dBi loss is equal to 2.7 dBi. Now, some cables don't have a good model that Excel can accurately come up with an equation. You'll note this, that one is the equation varies from the actual data, and that the R squared is a lot lower than 1. If this happens, then you want to go ahead and still plot the data in Excel manually. Then you'll manually draw a line from the frequency horizontal axis to the data, then to the attenuation loss, and then you'll be able to come up with a fair estimate of your value. Here's an example of the RG174 data. If we want to find the frequency at 100 megahertz, 1000 megahertz, with a cable length of 30 feet, take this data, you plot it just like we did above in the other examples, and notice that that's not a linear line, and it's not a nice curved line like the power line like the LMR data was. So you want to take the 1000 megahertz frequency, you'll take the line directly up from that, and then you'll come across and you'll read the data, the attenuation data here. So the result is 32 dBi loss per 100 feet. At 30 feet, you multiply that times 30 feet, and is equal to 9.6 dBi. Go ahead and add your two end connectors, and you'll end up with your total cable system loss is 9.9 dBi. If you liked this video, like and subscribe. Join SARA to start your hobby of amateur radio astronomy. Go to our website at www.radio-astronomy.org. Thank you.